Hello, welcome to the YouTube channel. Today we will read a paper about the wireless power transfer, like the wireless power transfer for your phone or your power bank, your tablet. The topic is the room scale magnetoquasistatic wireless power transfer using a cavity-based multimode resonator. Let's see, there are some concepts like what is about the magnetoquasistatic and what is the cavity-based multimode resonator. I will introduce them in this slides, this presentation, and this is the paper issued by the Nature Electronics in 2021. Let's see what will be addressed. The concept of the magnetoquasistatic wireless power transfer and the cavity resonator. What is the cavity resonator and the difference to your phone wireless power transfer? And I will address them. And also I will introduce the multimode room scale resonator. What is it? And the mechanism of its uniformly distribution in the room. It means the field, it can distribute the more even field in the room than the conventional methods. I also will show you the simulation for the human safety inside the proposed wireless power transfer room in that paper. And finally, I will give you the takeaway. Let's see about the concept. Magnetoquasistatic is about magneto. It means the magnetic related things or the electromagnetic field in low frequency, like tens of kilohertz to several megahertz. It's the alternative current, or so it will have the frequency is not the DC, it's AC. So it's the EM field, and it's the toroidal shape of the EM field nearby the AC or magnetic dipole. The magnetic dipole, just like a magnet on your fridge. Yeah. The AC field can be generated by the AC current, alternative current, or the rotating magnet. Yeah, if it spin, then you will have the AC electromagnetic field. So it's about the word magnetoquasistatic. Quasistatic is because it's in low frequency. It's when compared to the wave frequency like the megahertz or the gigahertz. And yes, it's about the magnetoquasistatic. And what is about a cavity resonator? Let's see. It's enclosed conductive structure, just like the figure below. It's consists of four walls like a box, and there is the enclosed circulating current. So it will, according to the right-hand rule, it can generate to the from in the center from the below to the top side magnetic field. And the wall itself, let's see the second point. The conductive wall, the conductive structure itself will conduct the AC as the transmitter. Transmitter means that from the power supply, like from the socket on the wall, then it will generate the electromagnetic field inside the cavity and to provide the field, so that if there is a receiver or your phone have the receiver, then it can receive the energy from via this wireless way to your phone to charge your battery. So this cavity resonator is a transmitter. It conducts the AC as transmitter. And at the third point, it will resonate to a capacitor and form a frequency, because there will be an inverter connected to this conductive structure, this transmitter. So there will be a specific frequency, but because there will be a resonate capacitor connected to this box, to this conductive structure, so it will be called as a cavity resonator. Let's see about the cavity resonator system. the resonance lower energy loss and higher gain, because for the impedance of electrical impedance, that if the operation frequency is at the resonate point, that the series reactive components will be cancelled, so that the power loss will be lower. So it means have a higher frequency. So they will use the resonator as the cavity transmitter. And the second point is the inductance is hard to acquire. We can see the picture here. It's just a box rather than the toroidal shape like the spiral or some coils, that the inductance is quite hard to measure. So because it's a plate rather than a coil, so we need to use a method conducted by the computational methods to estimate the parameter, the inductance of it, so that we can to decide the resonance capacitor for it. This method is called the finite element method, FEM. It's a computational way to estimate the inductance or the mutual inductance between the transmitter and the receiver. It's a computational way to have the wireless power transfer parameters. So in this paper, that they use the finite elements method, FEM, to get all these parameters. The linkage the frequency to the energy in the room. Yes, because it's a room scale. A room scale means that the people may use this room, that we will enter this room and to have variety of the conductivity activities. So it need to consider about the safety toward the people. So, but how could it to estimate the energy of the EM field, electromagnetic field, to the energy of each volume? So it uses the energy alpha in an inductor. Alpha equals to a half times to the L is the inductance of the cavity structure times the square of I, the conductive current. And 2 pi f equal to omega, equal to the 1 over root mean square of L times C, the inductance of the cavity structure times the resonate capacitor to it. Okay, so now we know the transmitter and the energy in the volume, that we also need to know about the receiver. We need to receive the energy transmitted by the transmitter to the battery or to a fan or a light bubble or the phone. So it's the receiver. It can be the conventional way. It can be the planar spiral or the helical solenoid, just like the conventional wireless power transfer. Okay, let's see the proposed room scale quasi-static cavity resonance in that paper. It's a 6-plane aluminum room cut by corner. You can see it's like a room, but the corners are cut. So there are some way for you to enter. The middle of the wall are split by the series resonance capacitors. You see that of each wall is not an entire plate. Rather than that, it consists of 2 plates with an air gap between, and then the series capacitor will connect these 2 plates and to conduct an entire closed loop circuit. And in the center of the room, there will be a copper pole to conduct the alternative current. You can see at the right hand side is the experimental room. The plates are the aluminum, and there are the signal generator and the radio frequency RF amplifier. For the mode 1, it is called the pole independent, PI. That the room will conduct the currents on its wall and without the pole at the center. So it's called a pole independence. Because the box is symmetrical, so we can just to analyze a quarter of it. Then another three parts are identical to that one. We can see that these two walls nearby conducts the AC in reverse direction. From the left hand side, the current is conduct from below to the top, and then it will go through the ceiling, and then to go from the top to the ground at right hand side. And then also at ground, it will circulate through the place on the ground to the left hand side to form a closed loop circuit. So you can see that the current density at each will be have a higher value than the center one. So what does it mean? It means that near the edge that it will have the higher currents, and also it can excite the higher magnetic density. At the right hand side is the simulation picture from the paper that we can see at wall. When the position is near the wall, that it have the brighter color than at the center. So it means that when you get more nearby the wall, that you will have higher magnetic density rather than to go to the center. This is the mode 1, pole independence. Conduct the wall only without the pole, and you will get a high magnetic density at the wall. And it is the second one, is the mode 2, pole dependence, also called PD. Is to supplement the former mode 1, that it will conduct the wall nearby in the same direction AC, and also conduct the currents from both wall to the center pole. And then you can see from left and also right hand side the wall, it will conduct the current from the ground to the ceiling, and then they go together, have the higher current density at the center. Why? Because the current itself is a fixed number, but when the circulating area at the middle is narrower than the outer side, so the inner position will have the higher magnetic density, and it will have the highest value at the pole. So you can see at the right hand side is the simulation of the FEM, that the center side will have the higher magnetic density. It will have the brightest color than at wall side. So combined with the mode 1, that the mode 1 have the higher magnetic density at the wall, whereas the mode 2, the PD, pole dependence, had the higher value at center. So combine these two together, we can have the even distribution. The multiple resonance mode combine these two magnetic density, ensure the wireless power transfer is high efficiency regardless the receiver's position. These two modes, because if they operate at the same frequency, they will interference each together, so they will have two independent frequency for PD and PI modes. For PD, pole dependence, there will be a frequency, whereas there will be another one for the PI, pole independence. The PD mode, currents only flow through the metal wall, and the PI is the current will flow through the metal wall and also a pole in room center. And here's the frequency for them. For the PD, the frequency is 1.2 megahertz, whereas for the PI, the pole impedance is 134 megahertz. Let's see the simulation conducted by the authors. That the figure A at the left hand side, it shows the efficiency for the wireless power transfer efficiency for the PI, the pole independence, that the at the outer side of the center, that you will have the higher frequency because you have the higher magnetic field. You use the the same input from the RF amplifier, the radio frequency amplifier, or from the power supply, you will have the higher magnetic density at the wall, so the receiver will gain more energy. Whereas in opposition at the center, you barely have none. So the efficiency around the wall is high for the PI mode. The figure B is the PD mode, that at the center, when you get more near and near the center, you will have the very high energy transfer efficiency. So combine them together. Let's see at figure C that the average efficiency of this room scale cavity resonator will be higher than just one to operate, and total efficiency exceeds 50% of 80% room space. It means that at the most place of within this room, that you will have the higher than 50% energy transfer efficiency. At right hand side, you can see is the simulation model that the receiver can put anywhere within the room, and there will be a drive coil of the PD mode, and drive coil PI mode is a simulation. The proposed wireless power transfer system, the dimension of that room is the width at 3 meters and length at 3 meters also. It's a square, and the height is 2 meters. The receiver coil is the 150 times 150 millimeter square coil, and it's a 6-turn helical solenoid, shown as the figure that it will also be series connected with a capacitor to have the same frequency to the transmitter or to the transmitters, for both PI mode and PD mode. The efficiency is higher than 50% at 98% of the space. Now, we have finished the energy power transfer and also the efficiency description, the system setup of that proposed idea for the cavity resonator wireless power transfer. So now we will look at the safety requirement for it. The safety requirement of the wireless power transfer, of course, it will concentrate on the magnetic field and also magnetic field density, as well as the electric field density. There are some safety requirements issued by the Federal Communication Commission (FCC) and also the Institute of Electrical and Electronic Engineers (IEEE). And also there are some other international requirements like ICNIRP. In this paper that these two are cited, so I will introduce them to you. The main concern of the magnetic field in this paper, the 1.3 or 1.2 megahertz, is the first one. The object inside this cavity resonator will be hit up by the field. It means the like the microwave. The concern of this magnetic field is to the rising temperature caused by the magnetic field, and also the second one is the electric stimulation. Electric stimulation, you can think like the directly excitation, like you conduct the currents, you touch a socket or a live wire, then you will be shocked, or you will have some stimulation, like the muscle will be get excited and your hand will take back. These two, or the most worst case is the people will be died, like the shock or some coordinate damage. There is a concept I want you to know is about the specific absorption rates, SAR in turn to the general public, is the average value for the whole body of us, the whole body of each people, the average value is 0.08 watt per kilogram. It means that for your whole body, if you are 70 kilogram person, and that the totally SAR of you cannot exceed 0.08 times 70. How much will it be? It will be 5.6 watt. The energy of the EM field inside your body cannot exceed the totally 5.6 watt. Is the first requirement. And the second thing is the localized SAR is cannot exceed 1.6 watt per kilogram. It means like your finger, that your palm and your finger, it called the localized SAR, localized, rather than instead of your whole body, or like your neck or your nail, your head is a localized place. The localized SAR could not exceed that value. So we will see how the efforts in that paper to conduct the estimation of the SAR. SAR requirement. Oh yeah, there are some additional information I want you to know. That, yes, there I mentioned before, the ICNIRP is the International Commission on Non-Ionizing Radiation Protection. It the requirement for the B field, it means the magnetic field, actually is equivalent from the electric field, because it's quite hard to observe or to acquire the direct impact from the magnetic field to an individual. So how could we to have or a way we can rely on to estimate the protection value is we just to take an equivalent estimation from the electric field. If at electric field that value will harm to the people, then we use their transfer to take equivalent value from the electric field to the B field. Yeah, so that's the main idea. The B field, it cannot directly harm you. Yeah, the estimation value is from electric field. Yeah, so the contact current stimulation. Yeah, I mentioned before. Yeah, you touch some currents or the live wire, and also it also mentioned another flow of the EM field is the heating up from the wave. And about like the cancer, the leukemia, or the effect on the pregnant, yeah, they are all analyzed in the reports, but there are no strong evidence to prove that there are some very direct or evidence to prove that. Yeah, so that we can say from that three institutes, the main concern on the EM field, the non-ionizing EM field, are two concerns. One is the heating up from the wave. Another one is the contact current stimulation. That's a picture I make myself. Yeah, there are three versions of the requirement of the ICNIRP, and one is from 1998, and another is 2010 and also 2020. That there are some contact currents like if exceeds like 30 milliampere, that you will get shock. You will have the shock hazard, and yeah, and also it's determined by the frequency. If the frequency is get higher than higher, that the heating from the wave will you need to more emphasize. Whereas at the low frequency, you just need to think about the contact currents. From this picture you can see is the requirements, and for the normal use 50 hertz like fridge or computer or something like that, they are actually quite safe because there will not be the heating up problem. You will just need to protect yourself from the contact current. Okay, let's talk back about the safety requirement of that paper. Yeah, it also do the FEM simulation again, the finite element method simulation. It do it again, and the results show the field density is far less than the requirements. We can see, yeah. At 6 dB, it means that 1.6 watt per kilogram, it will be red, but in this simulation picture, we can find no red area. And yeah, the minus 13 dB equals to a 0.08 watt per kilogram. It should be the orange color zone, but there isn't in the figure here. So in that paper, that proposed methods is quite safe the human. Okay, now let's conclude this paper and to give you some takeaway. The cavity resonance wireless power transfer WTT is a box-like transmitter system rather than a very small rig, a small transmitter or a small spiral, small pancake-like setup or rig. No, it's not. It's a box-like transmitter system, so that's why it's called cavity. The multi-frequency for multimode operation is to provide an even field distribution. Yeah, the first frequency it will provide the field near the wall, whereas another frequency will provide the magnetic density at the center of the wall. And superpose, it means add two density together that the room have the even distribution magnetic field. That's the multiple frequencies. About the receiver could be the conventional solenoid or the spiral design. Yeah, just like what exists in your phone now. Yeah, it could be the transmitter design itself will not affect your receiver. And the safety of non-ionized frequency are the thermal effect and the electric stimulation. For the low frequency electromagnetic field, and also perhaps there are waves. The FEM, finite element method, it can help to acquire the magnetic related parameters like the energy inside a volume, or the magnetic field, or the wireless power transfer efficiency. It's a computational way called FEM, finite elements method. Okay, I think about this paper, the room scale magnetoquasistatic wireless power transfer using a cavity-based multimode resonator is over here. And if you have more things want to know or have some questions, I welcome you to leave the comments below so I can answer them. See you. Bye bye.